Hey everyone, welcome to semester 2 of Math 2. I'm standing in my dining room creating these first couple of videos for you because I'm not at school able to make these videos before the semester begins. That's why I'm dressed the way I am, so forgive me for that, wearing my dad hat and my dad shirt and all that. But we're going to get into this unit that's really focused on simplifying radicals, dealing with the idea of radicals. So this lesson is about simplifying radicals. We're going to do other lessons that deal with adding and subtracting radicals, multiplying, dividing radicals, rationalizing the denominator, dealing with imaginary numbers. You'll see what all that looks like as time goes on. But before we get into that, we gotta deal with this lesson first, and that's simplifying radicals. But before we go any further, let's talk about what a radical is. A radical, when I say radical, what that means is just the square root symbol. That's a radical, okay? And the thing inside the square root, whatever this is, this number, variable, whatever it is the radicand, okay? So we have plenty of examples that we can go through. We could say, well, what's the square root of 25? And what's the square root of 81? And what's the square root of 144? And you guys should be able to rattle those off pretty quickly. What is the square root of 25? Well, what does it mean? It means what number times itself gives you 25. Now, most people will say, well, it's 5, because 5 times 5 is 25. And so if I ask you, how did you get that? I get a lot of students say, well, you just divide 25 by 5. Well, where did the 5 come from? How did you know it was 5? Because 5 times 5 is 25. In other words, 5 squared is 25. So you would hopefully agree with me that 25 is the same as 5 squared. And you can see here, we're going to get more into this in the future, we can see that the square root of 25 is in fact, we'll start off with this, it is in fact 5. But why is that? Because we rewrite 25 as 5 squared, and when I take the square root, notice what happens. The square root and the squared cancel each other out. They're called inverse operations, and you're left with just the 5, okay? Now there's something we need to add to that, because that is not the only answer. That's not the only number that when I multiply it by itself, I can get 25. You see, I could also say negative 5 squared. Negative 5 times negative 5 is also 25. And so we can also see that again, the square and the square root will cancel each other out, and we're left with negative 5. So in fact, we would say that the square root of 25 as a final answer is either 5 or negative 5. Not both, it's one or the other, okay? This positive one is called the principal root, right? And this is called the negative root, okay? Now, most of the time, you guys have only dealt with a positive version of this, because when we're talking about square roots, we're usually talking about the length of something or how far it is from one point to another point, and we can't have negative length. We can't say how far is it from here to there. Well, it's negative 2 miles. No, it's 2 miles. It may be 2 miles backwards, but distance is always positive. So that's why we focus on the positive or the principal root and kind of ignore the negative root. But as we get further and further into mathematics, this negative root is going to be important, okay? So let's go ahead and look at, my eraser's horrible here. Let's go ahead and look at the actual lesson and see how I wrote it out there, because I think that will give some insight into how to simplify radicals that aren't so easy to simplify. So remember, a radical expression is just one that has a square root symbol in it somewhere, okay? So again, the example that we just had was the square root of 25. The way I wrote it here is I said 5 squared. Another way to write it is to say 5 times 5. 5 squared is 5 times 5. And so you can see, because I have a pair of 5s, that one of those is the answer to the square root of 25. But we also say negative 5. And remember, we called the 5 the principal square root. I spelled principal wrong up there. And the negative 5 is the negative square root, right? So let's look at another example, a square root of 81. Well, that should be pretty easy. What number times itself gives you 81? Well, we'd write it out as the square root of 9 times 9, and therefore our answer is 9 or negative 9, depending on which one you want. Do you want the principal root or the negative root? The square root of x squared, that one's kind of weird, right? You have to kind of go back to what we had up here. Or remember, x squared is just x times x. And you can see that we're multiplying the same thing by itself to get to x squared. And so our answer here is just x. Now somebody might say, well, why isn't it negative x? Why did you just put x? In the other ones you put 5 or negative 5. And in 9 or negative 9. Why not x or negative x? Well, that's because we don't know what x is. X could be positive or it could be negative. So we don't have to represent the negative in a separate expression. The negative is found when we figure out what x is somewhere in the future. Okay? Now, let me go through a little story here. And this story is just to help us remember the process of finding square roots. And I gave you some easy ones here to start with, to work with. But we're going to go deeper with some more difficult ones later on. So let's take a look at like the square root of 36 here. The way I look at this, the square root of 36, is this is the story I tell. There's no basis in reality. It's just a fun little way to remember this. I call the radical symbol, right, the square root symbol, a prison. And what we're trying to do is we're trying to break out of prison, okay? And so the first thing we need to do is we need to break up the population of inmates into their gangs, if you would. And what I mean by that is, in mathematical terms, is I want to factor this, prime factor it. So you could either do the factor tree or the cake method. I'll do the cake method here just because, as a good example. So we'd say 36 is divisible by 2, and 2 times 18, or 36 divided by 2 is 18. 18 is divisible by 2. 18 divided by 2 is 9. 9 is divisible by 3. 9 divided by 3 is 3. And then 3 is divisible by 3. So 1 on top. There's your cake with a candle on it. There it is. So what I want to do is I want to rewrite the square root of 36 to have its prime factors instead. So it'd be 2 times 2 times 3 times 3. So there are my prime factors. Basically what I've done is I've broken it down to the simplest factors that I can, the prime factors. And in my story, these are gang members. And you're part of a gang if you're the same number. So we have the gang of 2s and you have the gang of 3s. Well, when you try to escape out of prison, and again, I'm not advocating for escaping out of prison or anything like that, it's just a story. But when you try to escape out of prison, you need a partner to try and escape with you. And so you can never pair up with another gang. You only can partner with somebody in your gang. So here we have a gang of 2s. We're going to circle those guys. And they're going to try and escape. The way they try and escape is they dig a hole under the prison and they try and escape. Now outside the prison walls is a guard tower. And on top of that guard tower is a guard. And that guard, unfortunately, has some sort of weapon to stop you from escaping. And so here's the prison wall here, right, with the barbed wire and everything else. And here's the prisoners. And these prisoners dig a hole underneath the prison wall, and they come out on top of the other side of the prison. And so one guy pokes his head up and sees that the guard isn't looking. And so he gets up and he runs for the forest. And so here's the forest over here. And he runs for the forest. Now, the guard sees him as he's entering the forest and realizes, oh no, I missed him. And so he looks back to where that prisoner came from, and he sees the second prisoner poking his head up out of the hole. And so he puts him down. He shoots him. And so this guy is no more. But this guy, he escaped into the forest. Okay? He is a free man. And so what happened? Well, up here, back in our story, or back in our math world, what happened was that the gang of twos, one of the twos escaped prison. So here's the prison. Here's the prison here. One of the twos escaped into the forest. That's why he's outside the prison. The other two doesn't exist anymore. He's gone. He was eliminated when he was found out. But you'd also say that we have another gang that's trying to escape here. We got a gang of three. We have the gang of threes, and they do the same exact thing. They try to escape. When they escape, one gets away, and the other one disappears. The other one is gone. And so the three gets out as well. And so these two are outside, and nobody is left in the prison. And so we put a 1 there to represent that, just like the cake method 1 here. You could put it times 1 here if you wanted to. But we can see that the gang of ones, there's no other person in there that can buddy up with him and escape. But anyways, so who got out of the prison? Well, the 2 and the 3 got out of prison, so 2 times 3 is 6, and the square root of 1 is just 1, so our answer is 6. And of course, we'd also say or negative 6 there, okay? Principal root, negative root, and you guys knew this, the square root of 36 is just 6 or negative 6. We knew that. I was going through the process here so you understand when we get to something that's more difficult, we know what to do with. So prison break. We prime factor it, we list all our prime factors, we circle pairs, one gets out and the other one disappears. They don't stay in the prison, they're not outside of the prison, they're just gone. Out of this, one gets out and the other one disappears. Okay, so we had a 2 get out and a 3 get out, so 6. 2 times 3 is 6. So that's prison break for you. That's a good little way to remember how to simplify a radical. So let's go through a few examples here of a little bit more complex numbers. Complex is probably not the best word for that, but a little bit more difficult numbers to deal with. And so let's see here. Basically the process, factor and look for pairs. One from each pair escapes, the other from each pair disappears. So for A, we have the square root of 75. Now you can spend a long time trying to figure out what number times itself gives you 75. And you're not going to get a nice, clean, whole number. And we'll talk more about that in a little while. But if we follow the procedure that we just talked about, prime factor, so we could do the cake method of the factor tree. I'll do the factor tree this time. I got 25 times 3. And then 25 factors to 5 times 5. And so our prime factors of 75 are 3 times 5 times 5. So there are my prime factors here. Now prison break, remember you need to have a buddy that's part of your same gang. So we have a gang of 5s here. So these two are going to try to escape together. And this 3 doesn't have somebody to try and escape with. There's not another 3, so he's stuck in the prison. And so we would say that we have the square root of 3 because that 3 is stuck inside. And then as the gang of 5s tries to escape, one gets away and the other one disappears. And so our answer is 5 radical 3, or we could also say negative 5 radical 3, principal root, negative root, okay? So 5 radical 3. We don't really focus again on the negative root until we get there. We'll talk more about that in the future. But that's how you simplify a radical. That's a good example there. Let's take a look at the next one. Actually, before we go on to the next one, let's talk about one more thing that I think is important. This is simplified. This is the simplified form. Simplified, okay? Now, if I want to estimate, because this doesn't mean anything in real life. If I said, hey, go grab a tape measure and measure off 5 feet, you would say 5 feet, got it. But if I were to say measure off 5 radical 3, you go, I have no idea what you're talking about, 5 radical 3. And so this doesn't really have any application to construction and real world stuff, but it has a lot to do with mathematics and deeper levels of understanding of math that do apply to real life things. So if I want to estimate this, well, we know some square roots that are nice, clean, whole numbers that are around 75. For example, we know the square root of 64. The square root of 64 is 8 or negative 8. And the next one we know is the square root of 81. The square root of 81 is 9 or negative 9. We can see that the square root of 75 sits right in between, or somewhere in between, not right in between, but somewhere in between the square root of 64 and the square root of 81. 64, 75, 81. Therefore, we can conclude that our answer is somewhere between the answers of the other two. So somewhere between 8 and 9. So we'd say it's approximately something like 8.5. Now, is it close to 8.5? I'm not saying that it is. I'm just saying that it's somewhere between 8 and 9. So when I say this, I'm just saying somewhere between 8 and 9. It may be 8.1. It may be 8.001. But I just want to recognize that it's somewhere between 8 and 9. Some number between 8 and 9. So this is my estimate. This is my simplified form. Okay? So pay attention to what I'm asking for depending on the verbiage or the context of the problem. Okay? So let's go ahead and take a look at our next example here, B. Boy, these markers. I have Expo markers that look like they're from the 90s or something when I was in school. All right, the next one was the square root of 72. The square root of 72, well, we're going to prime factor that. So I'll do the cake method this time. 72, 2 and 36, 2 and 18, 2 and 9, 3 and 3, 3 and 1. So my prime factors are 2, 2, 2, 3, and 3. Now, we circle pairs. Now notice we have 3 2's here. We can't circle all 3's. You can only try to escape in pairs because this is a square root. It's a square, 2 sides essentially. So we have a pair of 2's and a pair of 3's. And even though this 2 matches those, there's not another 2. So he is actually stuck inside. And so he's going to stay inside. The 2 that's not circled is going to stay inside. One of these 2's is going to escape. And one of those 3's is going to escape. And so this simplifies to 2 times 3 is 6. Why are we multiplying? Well, because we were multiplying here inside. So our answer is going to be 6 radical 2. We can also say negative 6 radical 2. All right. Now that is the simplified form. Now we want to estimate. Well, the estimate is figuring out values that we know right around it. So the square root of 72, I don't know what that is. But the number right before that I do know is the square root of 64. And the number right after that I know is the square root of 81. So that's 8 and 9 again. And so we'd say the square root of 72 is somewhere between 8 and 9. So on the previous one, I came up with the same answer. I had the square root of 75 is approximately 8.5. And it is approximately, but it's not exact. We're just saying that both of these numbers are between 64 and 81, so we know that their square roots are going to be somewhere between 8 and 9. Okay? Let's go ahead and take a look at one with a variable in it now. You go, I don't know how to do variables. It's the same thing. It is the same thing. So here we have the square root of c cubed. The square root of c cubed. I don't know how to do that. Yeah, you do. Because we're going to do our factor tree, if you would. What multiplies to c cubed? Well, c times c times c multiplies to c cubed. That's what c cubed means. From here, we're going to circle our pairs. We have a pair of c's and then a leftover c. So this leftover c has to stay inside the radical. And then one of these c's escapes and the other one disappears. So we're left with c radical c as a simplified form. Now we can't estimate that because those aren't numbers. We can't do anything with it. So we're just going to simplify the radical, and that's how we do that. Okay. All right. So again, looking over here, making sure we're good with this. Looks like all those answers are good. We'll talk more about this thing right here, the c is greater than or equal to 0 later. But pay attention to what I am asking for. Am I asking for you to estimate, or am I asking for you to simplify? If I'm asking for you to simplify, our answer should look like this, this, or this. If I'm asking you to estimate, your answer is going to probably be some sort of decimal result. Okay. All right, so here is some practice problems for you. Got 3 for you to do. Go ahead and pause the video and see what you can come up with from these. The third one is an application from prior years. You guys should recognize that as the Pythagorean theorem to find a missing side of a right triangle. So pause the video. When you're done, come back and see how you did. All right, for number 3 there, it says the square root of 120. The square root of 120, we're just looking to simplify this. The square root of 120, well, that factors, depending on how you do it. I'll do the factor tree this time. Let's see, that's going to be 4 times 30. 4 is not prime, that's 2 times 2. 30 is 5 times 6. 5 is prime. 6 factors to 2 times 3. So here are all my prime factors. So that is the square root of 2 times 2 times 2 times 3 times 5. And you're going to want to multiply all those out to make sure you get 120. 2 times 2 is 4, times 2 is 8, times 3 is 24, times 5 is 120. So I know that I factored correctly. Now I'm going to look for pairs. I have a pair of 2's. That 2, even though it's like those, doesn't have another pair. The 3 and the 5 are not paired. So they all have to stay inside. So what's inside the radical is 2 times 3 times 5. And outside, one escapes and the other one disappears. So we're left with 2 radical 30. So that is the simplified form of the square root of 120. Now, if I want to write that as an estimate, the estimate, well, the estimate, square root of 120, I don't know what that is, but I do know one that's really close to it. I know the square root of 121 is 11. And I know that the square root of 100 is 10. That means the square root of 120 has to be somewhere between 10 and 11 because 120 is between 100 and 121. So I'm going to write about 10.5. Now that's not very accurate because 120 is really close to 121. But I'm only writing it this way to represent that it's between 10 and 11. So it might even be better to say, you know what, let's not say 10.5, let's say the square root of 20 is between 10 and 11, because really this is probably 10.99 in all reality. Okay, so that's number 3 there. Let's go ahead and take a look at number 4. Number 4 has some variables in it combined with some numbers. So that should prove to have a little bit of a challenge to it, but not too difficult, I don't think. Okay, so we have 5x times the square root of 48x to the 5th. 48x to the 5th. So notice these guys are outside the prison. We don't want to mess with those guys. Those are innocent people. They're outside the prison. They never went to prison. They're not trying to escape because they're already out. We do want to try and deal with the 48x to the 5th. So let's go ahead and factor the 48, and I'll do the cake method here. 2 times 12, 2 times 6, 2 times 3, 3 times 1. So my factors are 2 times 2 times 2 times 2 times 3. And then dealing with x to the 5th, we've got x times x times x times x times x. We've got, we're multiplying x 5 times here. And then we have a 5x outside. Now we're going to circle our pairs. Well, we have a pair of 2's here. We have another pair of 2's. Oh, we have a pair of x's and another pair of x's. The 3's all by himself, the x is all by themselves, so they're going to stay inside the prison, inside the radical. The 5x is already outside. We've got a 2 that goes out, another 2 that goes out, an x here that goes out, and another x there. And so now we need to simplify all of this. We're multiplying all of those, and really 5x just means 5 times x. So I'm just going to go ahead and order these because multiplication is commutative. I can multiply in any order I want. So it'd be 5 times 2 times 2, put all the numbers next to each other, times x times x times x. That's the outside. And then the 3x is inside. So 5 times 2 is 20. X times x is x to the 3rd. And then we have a 3x inside. And that is our answer for number 4. Okay. Now number 5, if we were in class like normal, I would actually give you a few practice problems dealing with the Pythagorean theorem before we actually got into this. But just because we're trying to minimize what we're doing here because of our situation, we're gonna just jump into the Pythagorean theorem at this point. You should have seen this in the past, and if you haven't, we're gonna go back over it later when we get closer to the end of the year. It's gonna be a very important thing. But we're looking for the value of x, and we have a right triangle with a 3, a 9, and an x. So there's no radicals. I don't see any radicals here. So what do I have to do first? Well, I have to create some sort of an equation based on this picture. And if you remember the Pythagorean theorem, I'm sure you do, you may not remember how to apply it perfectly, but the Pythagorean theorem says this: a squared plus b squared equals c squared. Now it's important, I don't like teaching it this way, but your a and your b are your two legs, and your c is your hypotenuse. Your hypotenuse is the longest side of a right triangle. Your hypotenuse is always opposite to, across from, the right angle here. The a and the b are the legs. They're the two shortest sides. They're the two that touch the right angle or intersect at the right angle. So I don't like using a, b, and c, because if we use c somewhere else, it gets confusing. So what I like to do is I like to call this a leg, and this a leg, and this the hypotenuse, because that's what they are. And so the Pythagorean theorem would say leg 1 squared plus leg 2 squared equals hypotenuse squared. All right, so up here, we'll get more complicated later, but what are my two legs? My two legs are 9 and 3, so I would say 9 squared plus 3 squared, and then my hypotenuse is x, so I'd say equals x squared. And then we want to solve this equation, and this is the first time that we're going to be dealing with what's called a quadratic equation, or solving a quadratic equation. We've done simplifying quadratic expressions, but now we're dealing with quadratic equations, quadratic functions, because we have an x squared, if you remember that from last semester. So simplifying this, 9 squared is 81, 3 squared is 9, and then x squared can't be simplified. We'll add those together, combine like terms, so that's 90 equals x squared. And then we want to try and get x by itself. So how do I get x by itself? Well, I need to get rid of the squared. How do I get rid of the squared? I square root. Remember, I talked about that earlier in this lesson. The squaring and the square rooting cancel each other out. So you're left with x over here. But remember, whatever you do to one side of the equation, you have to do to the other. So since I square rooted this side, I have to square root the left side as well. So we end up with x equals the square root of 90. And depending on what type of answer I want, if I want an estimated value, we would say, well, the square root of 90 sits between the square root of 81 and the square root of 100. Square root of 81 is 9. The square root of 100 is 10. So the square root of 90 is somewhere between 9 and 10, so I'll just say 9.5. That's the estimate value. But if I want to simplify the radical, I have to find the prime factors there. So 90 factors to 9 times 10, and 9 is 3 times 3, and 10 is 2 times 5, and those are all primes. So then I can rewrite this as 2 times 3 times 3 times 5, and that's equal to x. Then we're going to circle our pairs. We have a pair of 3's there, and so one of those escapes, the other one disappears, and so you're left with 3 on the outside and 2 times 5 on the inside, and so we'd end up with 3 radical 10. And that is our answer. Now, it's important here, and since these are in inches, our answer would be in inches. That just means inches. We don't put the negative root here because x is the distance between 2 points. And a length, a distance, can only be positive. So we're not going to put the negative result there. So that is our answer for number 5. All right, with that said, that wraps up this lesson. Hopefully you have a good understanding of simplifying radicals. We're going to be using this principle throughout this entire unit. Every lesson that we do will have something to do with simplifying radicals. So it's absolutely essential that you understand what we do in this lesson and you're capable of repeatedly doing it and showing that you understand it. If you have any questions, comment below or reach out to me during tutoring or ask me during class, and I'd be glad to help. Have a great night.